A swinging bar. A thin, uniform 3.8 kilogram bar, 80 centimeters long, has very small 2.5 kilogram balls glued on at either end. See in the figure, you can see these two balls, 2.5 kilogram balls, are glued at the two ends. It is supported horizontally by a thin horizontal frictionless axle passing through its center, so this is the axle, and perpendicular to the bar. Suddenly, the right-hand ball becomes detached, so this is gone and falls off, but the other ball remains glued to the bar. Part A, find the angular acceleration of the bar just after the ball falls off. Part B, will the angular acceleration remain constant as the bar continues to swing? If not, will it increase or decrease? Part C, find the angular velocity of the bar just as it swings through its vertical position. Okay, so here's the situation. This ball is gone, so we have this ball remaining, 2.5 kilogram ball remaining. And you can see that we have the weight of the bar pointing down, but it's on the axle, so it has no torque effect, but this weight, mg, will have a torque effect. So this will start swinging, so it's going to be rotating like this. And the length of the bar was 0.8 meters. Now, we remember that for a uniform rod, the rotations about the center of mass will have a moment of inertia, capital ML squared over 12, which was done in problem 9.73. Now, the net torque that will be affecting on this bar at the moment the right-hand ball falls off will be, as I said, just due to the ball that remains to be glued on the left end. And R cross F basically gives us, this is the distance from the rotation axis, L over 2, multiplied with mg, and using the right-hand rule, we point from the pivot towards the application point of the force, curl our fingers towards mg, the thumb points in plus k hat direction. So we have a torque mg capital L over 2, because capital L over 2 is the distance, in k hat direction, and due to Newton's second law of rotational form, this will be moment of inertia for rotations about the z-axis multiplied with the alpha vector. Okay, now what is the total moment of inertia for this configuration? Well, we have the small m located at capital L over 2, so it's going to have mr square, capital M, L square over 4 contribution to the moment of inertia. And then we have the moment of inertia of the uniform rod, which is capital M L squared over 12. So the total moment of inertia will be 3m plus capital M parentheses L squared divided by 12. And this m is 2.5 kilograms, so it is 3 times 2.5 plus 3.8 kilograms, the mass of the uniform bar, multiplied with L square. L is 80 centimeters, 0.8 meters squared, divided by 12. So this calculation gives us 7.232 divided by 12, which is 1.808 divided by 1.808 divided by 3 kilograms meter square. So this total moment of inertia that we have calculated is for rotations about the z-axis. So it is IZ, the IZ that I put in this equation. Now we can substitute this result for IZ and calculate alpha, the angular acceleration. Alpha is equal to mgl divided by 2IZ. So it is mgl divided by 2IZ, and m was 2.5 kilograms, g is 9.8 meters per second square, l is 0.8 meters, divided by 2 times 1.808 over 3, and this gives us 16.3 radians per second square as the angular acceleration at the moment the right ball gets detached from the bar. Now, you can see that as this swings, when I reach the bottom here, this configuration, the weight of this ball will be also aligned with the rotation axis, and we have no torque effect due to that force at that point in time. So this observation at the bottom, the net torque will be 0 Newton meters. So alpha will be equal to 0. So alpha was 16.3 radians per second square in this configuration. It becomes 0 in this configuration. So we see that the angular acceleration decreases as the bar approaches the vertical position. Okay. And part C, now we want to know the angular velocity of the bar just as it swings through its vertical position. Okay, the easiest way is energy consideration. Initial potential energy of the bar is, when it's at its horizontal position, it's mg capital L over 2. Capital L over 2. Final potential energy is 0 joules. Initial kinetic energy is 0 joules. Final kinetic energy is 1/2 I total Iz omega final square. Now, let me check. Initially, we are at a distance L over 2 from the top. So we have, for this one, mg L over 2, the potential energy. That potential energy is decreasing to 0 at the bottom, and we are gaining a rotational kinetic energy as a result of that. So, and we have no friction in the system, therefore the change in potential energy plus the change in kinetic energy must be equal to 0. No friction, we have conservation of mechanical energy. Conservation of energy, or delta E mechanical, is 0. Now, the change in kinetic energy we can write as the final kinetic energy 1/2 Iz omega final square minus 0 is equal to minus the change in potential energy. change in potential energy is minus mgl over 2, and with the minus sign this becomes plus mgl divided by 2. These 2's will cancel, and we will be left with a final angular speed omega final mgl divided by iz square root. So if we substitute the numbers here, 2.5 kilograms, 9.8 meters per second square, 0.8 meters divided by our moment of inertia, 1.808 divided by 3, and then we take the square root. This gives us a final angular speed 5.70 radians per second. Okay, so in this problem we have a uniform bar which has a rotation axis. There's an axle, horizontal axle that goes through its center. At the beginning it's at equilibrium. We have two equal masses on both sides. Then one of the masses falls off and the bar starts swinging because there's going to be a torque being applied on this side, and that will cause a counterclockwise rotation. So the torque will be in k-hat direction. We want to know the angular acceleration of the bar just as this guy falls off, and what happens to this angular acceleration throughout the swing, and what is the angular velocity of the bar when it reaches the vertical position during the swinging process, so when it's at this position. So first of all, uniform rod has a moment of inertia ml squared over 12 for center of mass rotation axis, problem 9.73. We have a contribution from this m, lowercase m, the small ball, at a distance L over 2 from the rotation axis, ml squared over 4. So the total moment of inertia is the contribution from the bar, uniform bar, and from the small mass. And then the torque on this bar is not due to its own weight, because its own weight goes through the pivot, but the weight of the small ball, mg, applies a torque having a perpendicular distance L over 2 from the rotation axis, mg L over 2 in k-hat direction, and that's equal to I alpha, where I is the total moment of inertia, Iz. So this gives us an alpha 16.3 radians per second square at this instant in time. Now we see that when it goes through the vertical position, this mg will also be aligning with the pivot, therefore it will have no effect on the no torque effect on the bar, and so the net torque becoming zero according to Newton's laws of motion gives us a net zero angular acceleration as well. So we see that the angular acceleration is decreasing as we go through the swing, and at the vertical position it becomes zero. Now, what is the final angular speed of the bar as it swings through its vertical position? Initial potential energy is mg L over 2. Final potential energy is 0. Initial kinetic energy is 0. Final kinetic energy is due to the rotation of this bar, which is 1/2 I total omega final squared. So this energy is conserved because we have no friction in the system. As you can see in the problem, it's a frictionless axle. Therefore, we have conservation of energy. So this allows us to write omega final as mgl divided by iz square root, which has a numerical value 5.70 radians per second when reduced to three significant figures.